Hi everybody, let's go. I want to do a quiz on the complexity of algorithms. I know it's perhaps not the easiest of topics and might be struggling a little bit with it. I'll make it so that you have a couple of other extra points you can gain here and there by just analyzing a little bit what happens. So I'm going to give you two algorithms in pseudocode. I'll give them always in pseudocode because then it's clear what is happening. Okay, so how do you approach this? Well, you need to count the steps, right? So let's see. This is a single basic step that we have to do, and then we have a loop, and this loop will loop from 1 to 2n. Okay, and then inside that loop we have another loop that loops from 1 to 15. Okay, and then we have another loop that loops from 1 to n. Now, some of you might say, oh, okay, 3 loops, so our complexity is n times n times n cubed. Let's see. Let's see what happens inside that loop, the last of the loop. Oh, and I see this is a little mistake I made. Sorry about this. This has, of course, should have been indented. Otherwise, there's nothing happening here. So this has to be indented here. Okay, sorry about that. So inside that loop, we are going to redefine what t is. That is one single operation, that redefining. How many times do we carry out this loop? So we do this n times, right, from 1 to n. So this will be carried out 1 times n, so in total n steps. Now this loop, how many times we're going to do this? That's 15 times. So how many times are we going to carry out this part of the program? Well, 15 times we have to do n, so 15n. And then finally, this loop is being carried out 2n times. And so, allow me to go this way because I'm running out of a bit of space here. This has been done 2n times 15n times, right? Remember, in a loop, each time you have a certain amount of steps that you do, and then for each I, for 1 to n, what you basically do is you take this number of steps for I equals 1, this number of steps for I equals 2. So it's, if you want, you add 15n, 1 times 2 times plus 3 times plus 4 times 2n times. That is exactly 2n, 15n. So we see that this becomes 30n square, but then there's this extra one step, right? So in total, the complexity or the number of steps is 30n squared plus 1. But of course, we're not interested in this actual number of steps. We're interested in the complexity, and that is O(n) squared. That is quadratic. But if you, from lecture today's, you know that is actually, so it's polynomial time, and so this is tractable. It's good to see once in a while. Remind ourselves of what these things mean. Okay, so be careful. It's not just the number of loops that tells you that it doesn't make it polynomial and doesn't make it the degree of the polynomial. Why is this? What is happening? This loop is somehow a dummy loop in the sense of we do this for a fixed number of times. It might be that it's necessary. We're not saying this is a dumb program. It might be that we need to do this, but it does it in a way that does not depend on n, right? So this is of constant size. This is a loop of size 2n, but that is complexity n. This is also a loop of complexity n. So if you just have these nested loops, then it is the complexity of this loop times the complexity of that loop times the complexity of that loop. That's really what it is, O(n) squared. Okay. Now, here is a slightly different one, also with loops. So again, you say, okay, this loops n times and this loops, A while loop is always harder. Okay, this loops n over 3. Okay, and n over 3 and n, that's in complexity. So whether we take the floor, that's really nothing, right? That is just run in the decimals. That is no big deal. So, okay, this seems to be n minus 1, but it is the same as complexity n. This is complexity n. Question is, what is this? And for while loops, you kind of have to dig into the program and see what happens. So let's analyze this. I'm going to analyze this. It might be not immediately clear when you have such a situation like that. So it might be advisable to make a little bit of, take it an example. So I'm going to do the example. Suppose we run this on input 3. I'm going to take a small input because you see it's still a lot of calculations that to do. And what I want to do is keep track of my registers, the variables that occur in there. That is t, I, j, and k. So t, I, j, and k. And I will see what happens. So in the very first step, we're going to go this step only once. T is initiated, B0, and I, J, and K are still undefined. Okay, then we go to the for loop. Now when I have a loop, I'm going to start coloring these things. Let's start with orange here. So this is an orange loop. I indicate it that way. I'm not saying you have to do that, but somehow it helps visualize where you are, to keep track of where you are. You can do, instead of coloring, a numbering or something like that, yeah, line 1, line 2, that's very often used in computer science. Okay, so what happens here, we start a I loop, so I has to be initiated as 1. T is still 0, and the other two are still undefined. And the next step is an assignment. If something happens, there is J. Since that is inside the loop, I'm going to give it a different color. I want to keep track of what happens here. So that is 0 and 1. Now, J also gets defined, and J is 2 to the power I. That in this case, 2. K is still undefined. Okay. So this was a loop. This is a loop. Yeah, this is inside the loop. And now a while loop starts. So let's put this while loop in red. Sorry, I keep making this mistake. So, okay, this one up in red. And so, here's my while loop. I want to keep this in black. Of course, it doesn't do anything. It just does a check here. But let's see what it would do in this case. It's comparing 2 with 1. And it's not the case. So it carries out what's inside. That, unfortunately, is another loop. So we keep track of this loop. We have a for loop here. So this starts another loop in which k gets initialized. 0, 1, 2, and 1. And then we should always check whether we have not already reached this endpoint. Now, if n is 3, then this value is 1. So no, we haven't actually. If this would be, for instance, 0, this loop is not even carried out. Okay, but we have to carry it out, so we carried it out. That is, again, another step, which I'm going to color now brown, I guess. I'm still, oops, brown. Oh, why didn't it change? Brown. Okay, so that's inside the loop here. So this is where a T gets defined, and T is the sum of all the registers. Notice that at this point, all the registers, all the variables are defined. And it's just the sum of these. We just add all these up. This is T, 1, I, J, and K. So just the sum, that is 4. And everything else is not changed. Okay, that is the only thing that happens in this blue loop, so we have to loop back here. And what it means is in this step, the blue step, the next blue step, I gets incremented by 1, 2. J is not changing, K is not changing. K is incremented. Sorry, I said it wrong. It's the K loop, right? So K is incremented to 2. But it's compared then with this value, and it says, oh no, I stop. So we jump out of this loop. So it doesn't actually carry out the loop. It just jumps now and says, okay, go a level higher. The level higher is the red loop. And what does that do? It's now that is gonna say, is my sorry. No, sorry. No. I forgot this. There's one more step here. Sorry, because otherwise I would be in trouble because I would keep looping, right? Luckily, there's one more step here. I'm sorry, I missed that step. So we have to highlight this. I'm running out of all possible colors. Pink perhaps. This one. What is happening here? Okay, this is at the same level as the blue loop. The blue loop has stopped, and the blue loop says now, okay, you have to go to the next instruction that comes after me, which is this one, and that is changing J. So J is now changed from 4, 1, J is now changed to 1. And then K is still, the values, nothing else is changed here. Good. Then that's the end of the while loop. So now from here we have to jump back there, and what, I don't need to go back to this register. You go back to, I should perhaps indicate it better. Let me indicate it this way, right? We have to do, again, a while loop. So here comes this one. So we jump now to this one. Let's not draw errors, okay. What is happening here? Well, the values, nothing changes in this loop. It's just a check loop. But it checks now this number, and it says, oh, it's 1. I'm done. Bye-bye. And so it now tells me, okay, go whatever you have to do. Next, what comes after me? Nothing. In other words, I have finished this loop. So I'm going back to this loop here, but of course with new values. So let's see what happens here. So we are going to the here. This of course will be blank. So 4. What happens there is I gets incremented. 2, 1, 2. Nothing changes there. Only I has been incremented, and it's been checked against the bound, which is in this case 3 minus 1, 2. So it is legal. So we have to carry out this thing, and then we start over again. So we repeat the color problems, the colors as they are. So we start with green again. So what is in the green step? J gets redefined. 4, J gets 2 to the power 2. That goes now 4. And then K is still 2. That does not change. Then the while loop is being carried out again. You see, it gets kind of tricky, right? And we'll see, we're not there yet. We need to do a couple of steps. Okay, so where are we? The J loop itself doesn't do anything except it checks this number against 1. And it doesn't, there's not 1, so it keeps going. Right, what's the next thing? The blue. Blue is a loop itself, and in that loop, K gets initialized to be 1. So 4, 2, 4. This is now the place where K gets a new value, 1. And then what is T? What's the next step is then the brown one, right? In the brown one, T gets redefined, and remember it was a sum of all the registers at the current state of the registers summed up. That is 11. Okay, I repeat, this is just this sum here that we have to do. Okay, 11, and then the other registers stay the same. And then we says, okay, go back and go, I'm done. The K loop keeps going, but the K loop in this case never is carried out more than once, because n is 3, so it's from 1 to 1 for our value input of n. Of course, it's not true. It's not in the situation that we are in the previous case, where one of these loops had a fixed endpoint. This fixed endpoint is not fixed. If n gets bigger, we're going to do more and more times this K loop. All right, that's the difference. Okay, okay, keep going. So this means what? Okay, so as we said, the blue loop is only carried out once. So the next thing that happens is the step after the blue loop, which is the pink step. Hope the colors help you navigate through what I'm doing here. 11, and that diminishes J by 1. 2, 3, 1. Oh, I guess, yeah. Technically, what happens here? Sorry, I should say. What technically happens? K gets 2, and then compares to this, and they say, okay, it's jumps. I'm not going to write this up here. This is a step that here I wrote it down, but it is a step that nothing happens. The value of K is no longer important. So it is true that at this point perhaps K is 2. Okay, let's keep doing everything as we said it would be. Okay, so otherwise you might get confused. So this blue loop is carried out. It increments K, but then says, oh no, this is too much. I cannot do it. So now I'm going to the next step, and that is the pink step. Okay, that's where we were. Okay, so we have now 11, 2. In the pink step, J gets redefined, and this stays 2. And then we go back to the blue loop. No, sorry. And then we go back to the while loop. So we go back now. We jump back there, and we're going to compare now. So let me do this. Getting a little bit out of sight. So I'm going to have to do some acrobacy, juggling here. Let me juggle this thing. I'm going to bring this whole thing, if I can, down, so that we can keep track of what we're doing. Okay. Oh, these colors, sorry, have been accidentally dropped down, so these colors are not really part of the thing. Okay, now there's this line. Let's get a little bit of all these curves that I've been drawing here. That was not really necessary. Okay, so where were we? Yeah, the while loop. We were doing back to the while loop. In the while loop, nothing really happens. There's a test there, a comparison. Is this 1? No, it isn't. So now you carry out the next step, which is the blue loop. In the blue loop, K gets initialized to be 1. So That's why I was saying nothing happens really essential in this with this k here, and we know it's only going to be carried out once. So let's quickly do this. It carries out the next step. It's this brown guy, which is where the actual, if you want, the core, the meat of the routine is where everything gets added up. So we get 13, 16, 17. These two guys stay the same. It ends the k loop, so the k says, it hands it back to the k loop and says, okay, increment your value for k. Okay, it does that. It was actually light blue and I used time blue before. 17, 2, 3, 2. It compares this with the bound, which is too much. So it says, oh, okay, I'm done. The k loop says I'm done. So the next one can come pick up is the j, this pink guy, where j gets redefined. 17 to 2, 2. You see, it's tedious, right? Because what is happening is, what makes the while loop stop is this slight decrease. It is kind of a for loop, but I wrote it as a while loop. But something tricky is going on. But let's keep going. Where am I? So this is now carried out. So we go back to our while loop. So the while loop says, okay, guys, I know what you want to do. You want me to compare my j with 1, which isn't the case. So I'm going to hand it back to the k loop, the one that comes after me. The k loop says, okay, I'll happily take this from you, and I put k equal to 1, check it whether it's not equal to the bound, which it's not. When it's not exceeded the bound, it doesn't. It's actually equal to the bound. And so then I hand over to my subroutine, which is the calculation, the actual calculation where t is being calculated again. So we're here. We add everything that is 22. I hope I didn't make any mistakes in the meantime anywhere where I calculated. That's a minor thing. Don't worry about if I made a mistake there. Okay, so that's that. Nothing else here changes. Then the blue loops, the brown guy says, okay, that's as far as I'm concerned. So blue, you're up again. Blue says, okay, I know what I have to do. I have to increment my counter by 1 and compare it. Oops, it's too big. So I hand over to the next step available, which is the pink. Why keep I always hitting that one instead of this one? Which, what does the pink do? The pink decrement makes j 1 less, 1, 2. And then pink says, okay, I am done, so go back up to the while loop. And now finally, we're getting there, people, no despair. So 22, 2, 1, 2. It has to compare with this 1 here, and it says, oh, j is 1, I'm done too. So the pink loop says now I hand it over to whoever was working on me, and that was the yellow guy. The orange guy, I guess. So now we're jumping up all the way to the orange guy. And again, I'm in the wrong, I don't know, no, that's not orange. Sorry, Jesus. Okay, and what is happening there? Increment I by 1. So we get 22 I, which is I was my second one. So this one now becomes 3, and these two are the same. And then I compare 3 with the end part. Wait, yes, and yes, I compare 3 with this value, which is 2, which is too big. So this guy says, I'm done, guys. I'm done. I don't need to do next guy. There's nothing next anymore. It's the return. So we are at the end. So here we are. This is what it returns. It returns 22. Okay. Now, that's just to understand what goes on in this algorithm. But it also hopefully helps you see a little bit what is happening. How many times do we do the orange loop? Well, we see from 1 to n minus 1. Let's go. We already analyzed. The k loop will be, so if we talk about complexity of the loops, just this loop is complex. The complexity of the loop is carried out O(n) times. It's actually carried out n minus 1, but in big O it is carried out O(n) times. This loop is carried out O(n) divided by 3, or the floor of that, which is the same as O of n. The question was how many times is the while loop carried out. Now what is happening in the while loop? You see that in the while loop, where let's look at here is one of the cases where the while loop starts. Sorry, this is not. Sorry, here. The color was just, I lost one of my colors here from this move that I made. But if you look at back, this is where it happens. J gets defined here. This is where J gets defined 4. Sorry, it's actually here, right? I don't know. Let me not color this because I don't forget now what color this is. I don't want to go back there. Here, this is the start of this loop where J has been declared to be 4. What does this 4 come from? Well, that is we're taking an exponential here. And what happens then is, it looks like a while loop, but it actually is a for loop. It just loops from whatever value we have going down. Instead of going from 1 to the highest value, it goes from the highest value to 1. Right? Because that's exactly what happens. Right? It starts with its highest value, and then each time it diminishes by 1. It never skips this step. It never does more than this step with J, so it is really that. So it counts it down. In other words, the size of this, this depends on how big J is. Okay, so let's now analyze it a little bit more carefully. So again, this is one step. How many times is this step carried out? Let me erase now what is heavy on the lighter side. I want to do this over again, but now a little bit more carefully. Okay, this is carried out O of n times. Why? Because inside I only have to do it once, and I will do this n over 3 times, which in big O is just O of n. Okay. Then I do this one. Okay, perhaps let me not write O(n) yet. Let me just write what it is. So this was n over 3, or n over 3 floor, but let's not write the floor here. And then I have to do this one step here. So this whole thing inside here is n over 3 plus 1. And the question is, how many times do I carry it out? Well, I carried it out 2i times, because that's the value of J. And it goes down by steps of 1. So this whole thing, this whole thing is carried out, how many steps? N over 3 plus 1 times 2i. Now, I don't want to keep track of all these numbers that do not mean anything. So in big O, the big O of that is n. It's n. I'm not going to write big O, but I'm going to think of this big O. That's a bit the nuisance of big O, is that okay, I'm going to write it this way. Let me not write it with big O, but just say, as far as big O is concerned, this is the same as n. This thing is just O of n, right? And then times 2i. Now, this 2i, how many times is this? Well, this loop, the orange loop, is carried out n minus 1 times, but the problem is that the inside part, it has different number of times we carry it out. You see the first time, from the first time the loop is carried out, and where is the second time the loop is carried out? I guess that was exactly here. This is why my color disappeared. Yeah, here, that was here, right? So the first time it's carried out much less than the second time. You see, this is much, much longer until it's carried out the next time. And that is because the J gets bigger and bigger. The number of times that the inside, this number gets bigger and bigger, okay? So instead of multiplying here, what we have to say is we can only add everything. We can say for this is equal, so this is equal to the sum from I going from 1 to n minus 1, right? This is what this I loop does. And each time we do this many steps. The first time it's much less, the second time it's a bit more, the third time it will be even more. So we have to do this total sum here. Now, okay, there's a little bit calculation with sums. Now the sum of the first n minus 1 powers of 2 is actually a very nice formula. That is just, that is, if you look at the tables that are in the book, this is actually equal to this number. Okay, so for instance, you have 1, if n is, well, n was 3 here, okay, but let's take n is 5 to see a little bit more what happens. Then we would have, the first time, we would carry it out 5 times. The second time, we would, I from 1. Yeah, right. So the first time we would carry it out, I from 1, okay, sorry. My formula might be minus 2 here, but let's see. Okay, we have 5 times, this is I equals 1, 2, then I equals 2, 5 times 4 plus 5 times 8, this is I equals 3, plus 5 times 16, this is I equals 4, plus 5 times 32. Okay, so if we do bring the 5 out, it's 2 plus 4 plus 8 plus 16 plus 32, and that is equal to 20, 30, 62. So yeah, it is actually 2 to n minus 2. The formula is for I going from 0 to n minus 1. And here we go from I to 1 to n minus 1. It's not so important, of course. We know that this part is not important. It's this what matters. So in big O altogether, this is O of n 2 to the n steps. And what in other words, what this means is the inside this while loop is the one that has the highest contribution to the complexity, because it is basically it grows exponentially, how many times we carry it out. It's not a fixed amount of times, but it gets always bigger and bigger, and if you add all these powers of 2 up, times n, so remember this is the formula, n times the sum of the powers, and as I said, the sum of these powers, if you look in the formula, is just given by this quantity. The minus 2 is correct, but say you can ignore it because it is really about this complexity, n to n. So what is this? Is this tractable, intractable? It's an intractable thing because this is worse than exponential, right? So this is worse than exponential. Exponential would be 2n. It's worse than that. It's n to n. Although it's that n to n or 2n, it's basically as bad. Worse than exponential, so it's an intractable problem. Just to connect it to what we have seen about Pn versus Np. Okay. All right. So that's how you can prepare for the quiz. And I want to ask you one or the other. Also, make sure that you understand this calculating of registers. I might ask you to do this. It is easy, much easier than actually perhaps analyzing the complexity, and it helps analyzing the complexity. So it's some extra points that you can get there. All right? Okay.